This diagram shows the 1861 map of the riverbed in blue overlaid on top of a 2005 aerial. You can see the difference in channel width throughout the whole area. You can also see the shifting of the channel across the valley floor. The river has been in one place or another across the valley floor through time. But this diagram shows the conflict between what exists today as a straight narrow channel and what is the natural channel, the stable channel given the water and sediment supply from upstream, which has not changed dramatically. This sequence of aerial photographs taken in 1942, 1974, and 1995 near the Jimtown Bridge, which is shown in the lower right corner, shows the dramatic decrease in channel width between these periods. This is due to expanding agricultural land pushing into the river corridor, filling former floodplain and channel areas. All the complex off-channel habitat has been destroyed. But what's important to note is that the straight channel configuration is not natural. The tendency of this river is to be wider, such as shown in 1942. During reclamation, the channel area was reduced by half between that measured in 1861 compared to 2007. The area shown in 1877 was 1,800 acres. By 2007, that had been reduced to 600 acres, 1/3 of the original amount. Again, the river was across the entire valley floor, so these are very conservative numbers in the early eras. One of the things that played a part in this was gravel mining. This diagram shows the rates of gravel extraction between 1981 and 2000. As you can see, the rates got up to 1,000,000 yards per year, but averaged around 600,000 tons per year. This dramatically dropped off in the late 90s, early 2000s, allowing the channel to fill by itself naturally, which, once again, is moving things toward a wide and shallow channel, not the deep, narrow one that had been created and sustained by repeated gravel mining. This is what is at risk for landowners in the valley floor. These diagrams show the reach of the Russian River in Alexander Valley that is owned by Sire Industries. In 2007, these gravel bars, a lot of them were 14 to 17 feet above low water, whereas before they'd been skimmed 1 foot above low water. Over time, the channel's beginning to fill, and as these bars fill, the channel moves laterally, increases sinuosity, loses flood capacity, reduces flood protection for landowners, and reduces the ability to move sediment, which causes more deposition. A summary of the data collected between 1994 and 2007 shows the net aggradation or channel filling with sediment of 2.89 million cubic yards. Net bar aggradation is 1.9 million yards. That means that over 4.5 million yards of gravel exists 1 foot above low water. Note also that 1 million cubic yards was taken through gravel extraction between 1994 and 97, and that has to be added to the amount. So essentially, 3 million cubic yards has aggraded over the mined areas. Now, what are some of the effects of channel filling with sediment? This diagram shows the lower Alexander Valley from Jimtown Bridge upstream and some of the large gravel bars, which have between 1994 and 2007 increased in height anywhere from 2 to 5 feet to up to over 20 feet in some locations indicated in yellow. This has implications for moving sediment and floodwater, but also, more dramatically, this could cause channel avulsion, a rapid change to the wide and shallow channel of the original form. To demonstrate the risk of avulsion in this reach, we've taken the aerial photograph and topography of the channel upstream of Jimtown Bridge for several gravel bars. This area, the bars have come up anywhere between 15 and 20 feet, and vegetation density has increased as well. What's happened is that the flow is being forced in a narrower and narrower part of the channel, which, during a large flood like the 1995 flood, could cause the river to fill with sediment and avulse across the valley floor, and this will be shown in the following diagram. To demonstrate the risk of rapid channel change or channel avulsion from the deep narrow channel to the wide shallow original channel, we're looking at a diagram of 1877, the lower Alexander Valley reach near the Jimtown Bridge. You can see the bridge, the West Side Road. You can also see the river channel with the tight lines and islands, once again inferring that there's more sediment than the river can move. The next sequence of diagrams shows how channel change could occur and the risk of avulsion resulting from sediment filling the channel. This figure shows the 1877 channel in green overlaid on top of a 2008 aerial. Again, the Jimtown Bridge is in the right side of the photo. You can see that the river is wider in a different place and with the islands in 1877. So in this location, the channel had existed across the entire valley floor in many different locations and shifted and meandered back and forth to form the soils that agriculture now depends on. So you can see it's quite a bit wider, which indicates a different type of sediment transportability. This shows the 2008 channel now, with a narrow deep channel, high gravel bars, and areas of dense vegetation growth. This reach has a very tight area for moving bed load of the coarse sediment during a large flood, and it also exists down in the backwater area because just downstream of the Jimtown Bridge is where the constriction of the end of the Alexander Valley occurs. This means that more sediment can come in than can leave this area, and this is the area of deposition. The gravel bars have increased substantially in an area, forming a bedload constriction at where the arrows are indicated. This means that the channel has lost over 75% of its original capacity from the early 1990s. So if there was a flood of the size of the 1995 flood, it would not be able to move the coarse sediment load through this reach. So if this becomes a constriction and fills, it'll force water over bank. The next diagram shows what will happen in the case of a large flood occurring, such as the 1995 flood. As the flood rises and the sediment load increases, the constricted channel becomes plugged. Water finds a path over the overbank area to the west. This is rapidly flowing water, which then strips the soil off the land and lowers the elevation to meet the grade of the river. Gravel then is backfilled in, and when all said and done, the next morning one could wake up after a peak flood and not see the vineyards that were there prior to the flood event. After the flood, the area of overflow becomes a wide open gravel bar. The soils have been completely stripped along with the vineyards, and since the soil is gone, this area is not recoverable to agriculture unless soil is imported and the river is rechannelized. But this shows the characteristic of the river and its natural tendency given the water and sediment load coming in from upstream, which is something that nature provides and cannot be controlled by humans. So we have a big dilemma. This channel is not stable. Another problem with channel filling with sediment is an increase in the bar height and the change from alternate bar and straight pattern to a meandering and high point bars. This has driven a lot of lateral erosion. This sequence shows the map of 1877 as the start near the Geyserville Bridge, which is shown on the right of the map. The tight lines are the riverbed, and again the islands are poking out, indicating an overabundance of sediment compared to the ability of the river to move the sediment supply. This diagram shows the 1877 flood in green overlaid on top of a 2008 aerial photograph. You can see the dramatic changes in the width of the channel. The channel is far narrower, mostly due to agriculture and the Geyserville Bridge. But also, the islands are missing. But you can see large bars and a beginning of braiding by the increase in sinuosity, and actually a point on the left of the aerial photograph where the channel is now turning uphill against the gradient of the valley. This shows the present configuration, or at least in 2008, of the river at the time the photograph was taken in the spring. There's been a lot of lateral erosion since then down near the Geyserville Bridge and the next 2 bars upstream. The next sequence shows a projection of current conditions in 2008 with trends of meandering, the meandering process that's continuing to progress and evolve, and the potential loss of agricultural land around the river corridor. This diagram shows a 2008 photograph with projected changes in lateral erosion if trends continue with large bar buildup and lateral erosion by point bar formation. You can see agricultural land is lost, mature riparian vegetation is lost, and bridges and infrastructures are threatened. Actually, down near bar 9 at the right side of the photo, the Geyserville Bridge, erosion has progressed to the point shown on the diagram and riprap has been installed. This is the west bank that's eroded in 2010, showing the progress of erosion just in very small floods, less than 2-year recurrence. Caltrans has had to come in and install riprap, actually riprap that's designed to launch into the channel as erosion proceeds. This area has eroded up to 200 feet laterally, while the inside bar, shown on the left of the photograph, has built considerably. This is the future of the Russian River if the gravel bars are not managed and if something isn't done about eroding banks.